ready to look at question 3, and let's see what it has for us. We are told that here an experiment is conducted in which the relationship between the melting point and the number of carbon atoms of the alkane's homogeneous series is investigated. The alkane members in this experiment are all unbranched chain molecules. The results of the experiment are represented by the graph below. Now, when we look at the graph, the first thing that catches our eye, we can really go through is the title. It says here, the graph of melting point versus the number of carbon atoms. You know, the title always would tell you that when we have this word before versus, it tells you that this would be the dependent variable. That means it's a variable that should be drawn on the vertical axis. And the one that comes after the word versus, in this case is the number of carbon atoms, is actually really the independent variable. And our independent variable will always sit on the x-axis. Now, we are going to firstly start to look at, perhaps the first thing in this graph to look at would be to check my intervals, because I know here that I'm actually having the number of carbon atoms. So this is to say here I have 2 carbon atoms, I have 4 carbon atoms, I have 6 and 8. But you have to notice that in between here, because remember graph is drawn using a scale, we must have somewhere here midway 1 carbon atom. Here we should have 3 carbon atoms. So it's important to look at the scale to say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this bar here is broken up into 10 pieces. That would mean somewhere at halfway 5, somewhere in the 5 mark, we should have 1 carbon atom. So 1, 2, 3, 4, 5. So somewhere here we expect to actually have a carbon atom. I'll just use a black pen to write that, and it's important for me to write these things because I know in the questions they might require me to actually read off these numbers. So we are saying somewhere here we actually have 1 carbon atom, and that would mean the same is true when we look at this interval here as well. We are going to add the 3rd carbon atom. And we're going to do the same thing until we get to the last block. So here is going to be a 5. And here is going to be a 7. But now what do these numbers really mean? Well, they mean that we have the carbon bonded to a carbon forming a chain, and that chain should actually be unbranched. So we are saying that this should be the alkanes, meaning they should range from methane going to octane, because we have 8 of them. Remember, they are a class or a homogeneous series, as you'd like to call it. So they'll range from methane, ethane, propane, and so on. And we're saying all of them are unbranched. They should not have branches, these members. So what I'm saying is that when we are here, when we say we have a 1 carbon atom, this would mean that I can draw this such that I have 1 carbon atom, and because it's an alkane class, it's an alkane homogeneous series, it means it will be bonded to 4 hydrogens, and this will give me a methane. And if I have a 2 here, it means now I have 2 carbon atoms bonded together. So here is a carbon-carbon bond, and because it's an alkane homogeneous series, I only have hydrogens. Now you must notice here that when you look at the molecule with 1 carbon atom, there is no carbon-carbon bonding because there's only one carbon here. So we cannot bond this to another carbon because it's only one. We start seeing the carbon-carbon bonding when we have more than one number of carbons in there, because then they can bond to each other. And this actually, we all know that it will give us an ethane, because eth would mean two. And if we continue going on like that, then we go to 3 carbon atoms, we are going to have carbon bonds that should be 3 of them. And obviously we know that because it's an alkane, or the homogeneous series of the alkanes, the class of alkanes, it only will have hydrogen atoms, and we all know that this will be called a propane. And if we continue doing that, we go to 4 carbon atoms, we are then now going to have carbon to carbon bonds like that, bonded to 4 carbons. And again, this will only be composed of hydrogen molecules. And the reason is because we are told that this belongs to the class of the alkanes. And very interesting as well is that you have to notice that all these molecules are straight molecules, they're not branched. So here we're also going to have then a butane, because 4 would mean a but. Now all of them, they are straight chains, they're not branched. Well, obviously with 2 carbons and 1 carbon, you don't expect to have branches, but at least here we could have branches, but you can see all of them are unbranched. And this pattern will continue like that until you get to 5 carbon atoms, 6 carbon atoms, 7 and 8 carbon atoms, forming those long chains. So we can clearly see that our chains are getting larger as we are increasing the number of carbon atoms. We are forming bigger and bigger molecules here. So basically what we're doing in this experiment is that we start with a methane, and we actually increase its temperature and see and look at the point where it will change its phase from a solid to a liquid. And that is the boiling point. Basically, that's the definition of a boiling point, when our molecule has enough energy to then transform from a solid to a liquid. Now, so we look at that and we measure those temperatures to see when we have 1 carbon atom. So when we take the methane and increase its temperature, where does it start melting? And we do the same with 2 carbon atoms. So basically we take ethane, we also increase its temperature, look at its melting point, and so on until we get to octane. Now you would see here that I still have the same scale here. There will be 10 bars here for me, that 50 here. That means this can be broken actually into 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So I'm having increments of 5 here until I get to 15, increments of 5 until I get to 100, and so on until I get to 150. And this here should also be 200 then. Now we can clearly see here that, for instance, when we start heating up the methane, we actually start at a temperature of around about 180, negative 180 here. And when we then take a different molecule, which will be ethane, we heat it up again, we can see that we have at least the around negative 170 here. So you can see that when I have 1 carbon atom, my temperature is small, but when I start increasing my number of carbon atoms, my temperature actually starts increasing as well, because we have 170. And when I have 4 carbon atoms again here, you can see that the temperature has increased significantly from the negative 180. And this is an observed pattern where you can see that even when you have 6 here, it has increased. And by the time we hit octane there, we have around about negative 60 degrees. Look at that. So the temperature is actually the highest. We require a lot of temperature to actually start changing the phase of octane from a solid to a liquid, to start melting it, right? Now, this is an expected result because we know that when we have a molecule that has only one carbon atom, there is the smallest number of bonds in it, and also the density of this molecule and the molecular mass. If we calculate the molecular mass of this using the periodic table, will be small compared to when we have two carbon atoms, because we have a lot of bonds here, we have a lot of molecular mass and density, and as a result, um, you know we then now have a larger molecular mass when we calculate this from the periodic table. And you can see that the same is true. Here we have even bigger molecule, a lot of bonds. Same thing here. The bonds are forever increasing, and therefore the molecular mass and the density of these molecules is getting bigger. Now that would mean that if we were to try to change their phase by increasing temperature, these bonds here will require a lot of energy, for them to actually start moving and changing this to be much more like a fluid, right? So the intermolecular forces, or what we call the van der Waals forces, will be much more larger on a larger molecule compared to a small molecule. It will take much more effort here to change its phase compared to when we have a one carbon molecule or a smaller molecule. However, the other thing that we have to notice here is that all these points here, they are actually following a trend. They have a clustering that shows an increase as we increase the number of carbon atoms. And that is an expected result, as I was explaining, that larger molecules will require more energy, will require more temperature for them to change their phase, for them to melt. But you will notice that point A here, which actually is a propane, it doesn't fall within this clustering. It doesn't follow the trend of increasing. It's outside that trend. And this is usually an expected result when you're looking at data points or doing experiments on data point. We see this a lot, or we learn these techniques a lot in mathematics, where we have one point that wouldn't follow a trend, or even two sometimes. And we then say those points, we can ignore them, or they do not affect the trend, because it's only a few points, and we call those things outliers. They do not follow the general trend. They are outliers. They're sitting there alone and have their own trend. So very important to notice this here, that our propane is an outlier. So what it simply says is that it does not conform to the idea that when you increase the number of carbons, the melting point will also be higher, because here we have 3 carbon atoms. We expect that the temperature should be higher, but actually is the smallest. So it doesn't follow that trend. So something just to look at it, and to say it is only the one point that is doing that, so it doesn't affect the whole trend. I hope that the explanation makes sense here. And what actually I have done, we call that problem interpretation, what we call the I rule, right? So this is the first thing that we do when we solve problems. When we call this the I rule, the interpretation of the problem. The other thing that I will do before I can continue with this question is that I will classify this problem as a problem that requires the knowledge of organic chemistry, and particularly looking at the specific section that looks at the physical and chemical properties of organic compounds. That is a section that looks at things such as boiling point, melting point, intermolecular forces, and so on. So that's the second thing that I'm going to do, classifying this problem to say where does it belong to. So that is the C rule, classification. Then we can jump to the third rule that we call the A rule. The A rule says problem answer. So basically now we are going to answer our problems, because remember, we have an extensive understanding at this stage, because we have interpreted, we also have classified. And classification is important because it helps us to focus on specific things. We're not going to run around inorganic chemistry trying to look at what knowledge can we use to answer this problem, because organic chemistry is also a large topic. So sometimes when you classify, you narrow down where you should focus when answering these questions. You don't get distracted or lose focus. And obviously, with question 3.1, we can all clearly see that we are requested here to define what a boiling point is. And as I said, even when they ask you these questions, you expect them because already you classified this problem to be around boiling point, melting point, and all that. So here we are required to define what a melting point is. I mean, when I was interpreting, I already defined this, and I pretty much said that the melting point is actually the temperature at which the molecules of a solid have sufficient, they have enough thermal energy to overcome the intermolecular forces. The intermolecular forces, and are then able to become a liquid. Now, this type of a question, we call it conceptual question. In other words, it requires you to have memorized your theory or know your theory. And actually with organic chemistry, we mostly get conceptual questions, meaning questions that focus on theory. We don't do much of calculations in organic chemistry. So when you deal with this type of a question, after writing it down, it is important to go through it, really look for spelling errors, and also check if this sentence is right and correctly. And then you can then move to the next question. When you do that, we actually call that the problem navigation. So that is the last rule that we apply on our problem solving strategy, what we call the academic constitution. So this constitution is made up of these 4 letters, ICAN, that reads I can, meaning when you follow this, you can solve this problem or even any other problem. So you navigate the answer by looking at it. So here we're saying that we are looking at the temperature at which the molecules of a solid have enough thermal energy. Now remember that thermal energy is like heat energy. So that's why when you increase that temperature, you're actually putting in heat energy in that molecule. When that energy is enough, it's sufficiently large, it will then overcome the intermolecular forces. That means that it overcomes the forces that are between the bonds, and when it weakens those bonds, the molecule will then start moving from a solid to a liquid phase. Right, it becomes it melts, actually it becomes molten. Then that's where we know at that point that temperature is the actually melting point. Now this is 2 marks to give this statement, so very important. There are other ways in which one can define this. You are more than welcome to define it in any other way that you understand, as long as it will give you that 2 marks. Now under question 3.2, they say write down the IUPAC name of the compound with melting point of negative 180 degrees. Now that is 3.2.3, so we're looking at 2.3.2, 3.2.1 I mean. Now when we go to this question, what we are told here, basically we're going back to our graph and interpreting it. We are told that the temperature here is negative 108, and we can see here that the negative 108 will actually sit below the 150, because remember we're going to have 55 here, 60, 65, 70, 75, and 80 would be somewhere here. So our negative 180 is actually here, and we're going to read this off to say when we have 108, we actually hit this point here. But now, how many carbons do we have? Because the number of carbons here will actually give us the name of the compound we're dealing with, the IUPAC name of the compound we're dealing with. And we can see that it is only a molecule that is made up of one carbon atom. It is exactly this guy here that we spoke about, the methane. So it means the IUPAC name here should be methane. I thought this is a very interesting question, the way they've actually also phrased it, because they say IUPAC name, and I know one would start thinking about rules and all that. Not necessarily. The name is there on the graph. It is still an IUPAC name, even though we don't follow the rules in this case. We can read it off the graph. And this is only just 1 mark because, it's a question that requires you to test your skills of reading graphs. When you did experiments in term 1, you were trained to read, to draw and read graphs, to do skills and all that. So that's what they're doing in this question. So again, when you navigate this answer after writing it, to ensure that the spelling is correct and everything is written correctly, and check for mistakes. That's what navigation is all about. Very important. It's very important to have that habit of checking your answers before you move to the next one. Don't just jump to the next question. Under 3.2.2, they say write down the melting point of heptane. Now, very important for us to understand that heptane is actually made up of 7 carbon atoms. So that means we are going to go to the number of carbon atoms where there are 7 here. And we are going to do the same thing here. But in this case, we start off with the number of carbon atoms to say we are having 7 carbon atoms. And what is the temperature, to say, of these carbon atoms. And when we read this off, we can see that we're going to have 55, 60, 65, 70, 75, and 80. So that means here we're going to have a negative 80 degrees. So our temperature here, the melting point, which is the temperature really, is going to be 80. So we are on 3.2.2, and we're saying we're having a negative 80 degrees Celsius. And very important to also report your answer with the units there of temperature. Now, when you do that, I'm navigating basically. I'm checking if I've answered the question. I've put the negative, I've put the number in the unit there. And this would give me 1 mark as well. We then move to the second part of the question that says to us that a point A does not conform to the observed pattern of scattering of points, and it is called an outlier. As I'm reading this statement, I'm smiling to myself because I actually said this thing said exactly this statement when I was interpreting my problem. I think you should be able to do that, especially because you've done experiments and you have interpreted graphs before. We already said that we have an observed pattern here. The scattering of our numbers are going up like that, but A here is an outlier, does not conform or follow that pattern, and we call that an outlier, right? Okay, let's see what question are they asking us around that. They then say to us here on 3.3 to say write down the name of the organic molecule in point A and state 1 use of this alkane as a fossil fuel. Now, let's start first by looking at the name. Obviously, we can see that this molecule actually has 3 carbon atoms. It actually has 3 carbon atoms. That's where you get your A there. And because it has 3 carbon atoms, we're going to say it's a propane, right? Because we know that propane is the one that has 3 carbon atoms in it. So the name of this molecule would really be a propane. We are on question 3.3. So we are on question 3.3, and we are saying that we have a propane. Now they say we should write one application of this molecule in real life, particularly as a fossil fuel. I don't know if you know this knowledge or not, but I'm going to share with you to say that, the tanks that we normally would buy, there's these tanks that we buy that contain gas inside of them, and that gas we use it for cooking. We normally would connect that gas to a stove for cooking, and inside these tanks there is a gas here that basically we use for burning, and we burn it through a stove and we cook using that gas. And that gas is a fossil fuel that is called propane. So inside of that tank is a gas called propane. Some of this, it's actually butane. So either butane or propane, and we use that for cooking. So that's simply your answer. And this gas is stored inside as what we call LP. It is stored inside here as what we call LP. LP would mean liquefied petroleum, liquefied petroleum. So the LP would stand for that. We store it as a liquid inside here, and we use that for cooking. So the answer here would be propane. Propane is used as LP gas for cooking. That's simply your answer, and this is just 2 marks because you get the 1 mark for naming the compound and giving one use. I don't know, do you know of any other uses that maybe your teacher has shared with you in class that you can share with me? I would love to know those. If you can leave them on the comments, as a comment there, for me to learn about them, and also to share maybe with your peers. Now we go to question 3.4, which is the last question, and they say to us here we should explain why the melting point of octane, which is at negative 60 degrees Celsius, is higher than that of butane, which is at negative that. So when we look at octane, we can see that is the last molecule we're dealing with here, and our octane here would be marked. We'll read it off here at this point. Let me do this properly. Our octane would be at this point here, and it actually, with us saying here that it gives us a temperature of negative 60 degrees. I can see that, it's just 5560. We also have butane. No, where am I going? We also have butane, which is 134. So butane would be made up of 4 carbon atoms. It's somewhere here, and we are marking here, they're saying negative 134. Okay, so that's what they have read there. Maybe just to check, I can say that this is like 105, 110, 15, 20, 25, 30, 35, 34 would be somewhere there. Now we want to know that why is the melting point higher for octane than that of butane? Obviously, you can see that octane would be a large molecule. Octane would be made up of 8 carbon atoms. It would be a large molecule compared to the butane, which is only made up of 4 carbon atoms, is a small molecule. So that's the first thing that I'm going to reason here. To say, when we are on 3.4, I'm going to say that the octane has the largest number of carbon atoms, the carbon to carbon atoms, compared. So here it's very important to compare because we're not looking at one molecule but two compared to butane. That's the first thing. The second thing that I will say here really is that because of octane is a large molecule, it will then have a large octane, it will then have a large molecular mass. Octane has a larger molecular mass and density than actually butane has, than butane. You know, when you go to the periodic table and you try to do the molecular mass, you calculate the molecular mass of octane, you would see that octane would have a much larger value of molecular mass than actually butane has. And even the density, the density of octane, because it has a large mass, it will have a higher density. Now, all these two information that I've written so far means that the van der Waals forces, forces, these are the forces between bonds, the intermolecular forces, sometimes we call them, right, that are between the octane molecule are also larger than in butane, molecule, would say, than in butane molecules. And we can then conclude to say, therefore, more energy is needed to move the octane molecules. And the melting point will therefore be higher. Remember here, we're not really reacting these molecules, we're just changing their phase from a solid to a liquid. So basically we are just moving, we're making that molecule to be much more elastic, maybe if the way that I can move, so that it is much more of a fluid and it can move. So it will require much more energy to do that. I tried to write this in point form because I noticed that this question is marked out of 4. So you need to put the 4 points. And these are actually your 4 points to say, firstly, we have a larger molecule compared to a small molecule. And because of large molecules will have a larger molecular mass and density, that also will give you another mark. Okay, so I am actually doing this wrongly. It should be 1 mark there, 1 mark here. And obviously large molecules have a lot of number of bonds in them, and that would mean that we require more force to actually make those bonds weak, right? Would require much more force, the intermolecular forces, and that means we're putting in more energy when we have a larger molecule compared to a smaller molecule for it to reach a higher melting point. And that's why it requires a higher melting point, because you do a lot of work. You have to increase the temperature until it gets to a large number where those molecules actually can start melting. And that's what we're seeing here, that we're doing a lot of effort when we have octane, because the temperature is much more higher compared to when we have something like butane or even methane. Look at methane. Methane at only 108 already is melting, but butane or even this at only 134 is already melting. But with octane, it takes a much higher temperature. You have to heat it. Even the time that you're going to heat it will take longer as well. We are going now to move to question 4 to close off this question paper.